10%. So what's the maximum speed up I can get? Factor of 10. Right? I went from 100% down to 10%. I got a factor of 10 speed up. No matter how many processors I throw at it, 10 is as good as I can do. Okay? Is that good or bad? Is it worth throwing a jillion processors at that problem?
No.
No. Because the return on that investment is pathetically bad. Right? I'm going to throw a modest number of processors at it because any more than that is not worth the money I paid for those processors. Somebody else could be using them to do something else. Okay, next slide. Okay. So here's sort of the picture of that. It's sort of logarithmic in the vertical there, and in the horizontal for that matter. But as the serial fraction goes down, the maximum speed up goes up in a very simple relationship. Next slide. Okay. So here's an example of that. I told you Fortran programmers that you're screwed, so I'm going to skip to the C version. Okay. So I've got some big array, I've got some scalar, I've got some index variable. I input the value of the scalar, and then I set the array to the value of the scalar times the index. I know that is not interesting and doesn't do anything useful. I'm just showing you that. Also, I left off a semicolon because I converted the Fortran code by hand.
Fortran doesn't have semicolons.
Fortran is allowed to have semicolons. All right, anyway, but you can see that the red bit ain't going to speed up. Right? Next slide. Good. So what do you want to do to get maximum speed up from the code that you're trying to parallelize?
To move it in a way so you can maximize and move things around the series.
Right, you want to maximize the fraction that can be parallelized. Now notice, it's not the fraction of lines of code. You could have 99% of the lines of code not be parallel, and 1% of the lines of code be parallel, and get huge speed up, as long as you spend 99.99999% in that 1% of the code. Okay. By the way, you're not going to actually get that amount of speed up, because there's an overhead cost associated with doing the parallel. Now, our goal is to get what's called linear speedup. Linear speedup means if I throw n processors at the problem, I will get a factor of n improvement in my performance. Right? So if I started at 100 seconds and I throw 10 processors at it, I end at 10 seconds. I got a 10x speedup. Okay? What is the probability that you will achieve that in real life? Pathetically low. By the way, it does happen. In fact, it even occasionally happens that you get what's called superlinear speedup. But don't count on it. Very rare. Next slide. Okay, so here's the concept. Scalability means as I throw more processors at it, does it keep getting faster in a reasonably close to linear way? The farther away the speedup is from linear, the less scalable my code is. Because if the overhead starts to dominate, the overhead of doing it in parallel, then I can't keep throwing more and more processors at it. Amdahl's law is usually one of the things that governs that, although not the only one. All right, next slide. Strong versus weak scaling. So my opinion, as a practitioner, is that strong scaling is weak, and weak scaling is strong. So strong scalability means if I take the same problem size and I throw processors at it, the time goes down in a reasonably close to linear fashion. Weak scalability means if I keep the problem size per process or per thread fixed, then the time it takes to do the problem stays roughly constant. I really like weak scalability, because I really like doing bigger problems. Next slide. Okay. So that particular one is showing weak scalability, making the size per problem, size per thread, or in this case process, stay the same. Total problem size goes up with the number of processes or threads. Next slide. Okay. Granularity means how big is the chunk of work that each parallel flow of execution is doing. A good rule of thumb is the coarser your granularity, the better your speed up. Why would that be?
Consequence of Amber's law.
In what way?
I mean, you're going to have less communication, or everybody's going to concentrate working in a big chunk of.
Right, so if you're spending all your time thinking about your own work and very little time thinking about everybody else, you're going to get your work done quicker. Because the time you spend thinking about everybody else is wasted. How many of you had that experience in grad school? So we like coarse grain as a general rule. Next slide. Overhead. Parallelism is not free. Those of you who were in the talk yesterday morning, when we did the jigsaw puzzle, got to see this, that there is contention for a shared resource, typically storage, usually RAM, and there's communication cost to get the different flows of execution, in this case the threads, to coordinate together. Right? And then one other that we'll talk about later called synchronization, which is, I don't trust you to be done with the work you need to finish, so I'm going to sit here with my arms folded and I'm going to wait until you're done. Thanks for making me waste my time. That is actually synchronization. Next slide. Okay, let's talk about shared memory. Okay, next slide. Good. So this is the jigsaw puzzle analogy we did yesterday, but not everybody was there. How many of you were there yesterday? A modest number. Good. Well, I'm going to describe what we did, because I don't have the jigsaw puzzle here. Next slide. Okay. So I've got a puzzle of 1,000 pieces. Let's say I can do that puzzle in an hour. Is that reasonable?
No.
Say yes.
No.
Thanks so much. Stop being obsessed with reality. Okay. Now if I have a Confederate, next slide, sitting across the table from me, how long will it take the two of us?
2 hours.
It depends. Thank you. All right, you got the takeaway for the day. That's good. Give her a big hand.
Congrats.
Good. So, some of you are not sure why you're clapping. Everybody clap for me for no reason.
Yay.
All right, can we just stop teaching this OpenMP stuff and I'll just do that for an hour? Oh, stop it. Don't encourage me. All right. So here's the problem. We think it would be half an hour, right? Same amount of work, twice as many workers, should be half the time, except every so often, the two of us are going to stick our hand into that pile of puzzle pieces at the same moment, and we're going to have to go, after you, no, after you, no, after you, or whatever, right? And that's going to take some time. We call that contention for the shared resource. Now also, when I finish my part of the puzzle and you finish your part of the puzzle, we're going to have to work together to get them to join. We're going to have to communicate at that shared interface. So that's going to be an overhead. Next slide. So maybe one can do it in an hour, two, maybe it's 35 minutes. Get four of us together. Does the contention go up or down?
Up.
Does the communication go up or down?
Up.
Okay, so the overhead cost is growing. So now I'm not going to be doing it in half of 35. It might be 60 minutes, 35 minutes, 20, 25 minutes, somewhere in there. Let's call it 22 minutes for the four of us to do it. Next slide. Uh-oh, now there's 8 of us. Contention going up or down?
Up.
Communication going up or down?
Up.
Okay, so I went 60 minutes to 35 minutes to 22 minutes. Now I'm at 21 minutes. That wasn't really worth the extra 4 threads, was it?
Nah.
Not really. Okay. So you can see we're getting a diminishing return here. Empirically, what we've seen in computing, by the way, in computing, what are the workers? Processors, cores, right? By the way, what's a core?
A fancy word.
Okay, I'll come back to that in a second. Okay. So in computing, what we've seen empirically is as the number of processes goes up, or threads goes up, in the shared memory configuration, usually somewhere in the 8 to 32 thread range, you'll top out and there's no point in adding more. Now, it's not always that high. Sometimes instead of 8 to 32, sometimes it's 4, or 2, or 1. Sometimes the serial version is faster than the best parallel version. By the way, I'm here to tell you, if you want to do supercomputing, how many of you want to do supercomputing? You are doomed!
Yay!
But it's fun. See, I like your attitude. Okay, next slide. So what I could do instead is I could split us up. I'll go sit over here. My confederate will go sit over there. Now, is the contention compared to when we're sitting together, is it higher or lower? How much contention is there? None. You've got your resource, I've got my resource. On the other hand, communication, what about that? What do I got to do in the literal case of the jigsaw puzzle? What do I have to do to bring our halves together, now that you're way back there? I'm going to have to actually pick up the table and drag it over there. So the cost of that individual communication is going to go way up. On the other hand, am I tempted to communicate often and unnecessarily? Not at all. How many of you had this experience in grade school? You used to sit next to your best friend, and then one day the teacher said, "You, sit over there." How many of you had that experience? Right, the rest of you are lying. Why did your teacher make you sit over there?
Communication more difficult.
Because you were spending a lot of time communicating, which meant that reduced the amount of time you had to work on your task. By splitting you up, that eliminated the temptation to communicate with that person. All right. Next slide. Okay. So we can start doing this bigger and bigger. This is called distributed parallelism. Next slide. Okay. One of the things we got to worry about is whether we're getting the balance between you and me correct. Right? So, should I give you twice as much work to do as I'm going to do? How many of you vote yes? How many of you vote no? How many of you vote it depends? Oh, good. What does it depend on?
If you're at the edges.
How good you are, and in particular, how fast you are at doing the work. All right, so suppose that I work exactly the same speed as you. Should I give you twice as much work?
No.
Why not?
Because we'll have
You
to
have
wait.
to wait for the person.
So, by the way, I agree. I even agree that it's bad. Now prove that it's bad.
You'll have to wait for the person that has twice as much work to get done.
So what? By the way, I agree, and I even agree with the facial expression that you're now giving. But tell me specifically why that's bad.
You just lost money.
So what could we have done instead? What would be the benefit of that?
Less time.
Ah! So if I originally gave you twice as much work as me, and we're working at the same pace, it could have been, right, I'm going to finish, you're going to be still working hard, I'm going to be idle. It could have been that we could have given some of your work back to me, in which case you would have finished earlier, which is what we want, because the time for us to finish in the minimum amount of time, for the time for the two of us to finish is the time for the later of us to finish. So what I want is, it turns out, the minimum amount of time is the time when we end at the exact same moment. So my goal is to get us to stop at the same time. So now suppose you work twice as fast as me. Should I give you twice as much work to do? Yes. Because then we'll finish at the same moment. Next slide. By the way, we call that